So a couple of people asked me a little about that. So I've added more detail on that. So before I sort of continue with kernel algorithms, I'm going to talk a little bit in more detail about how to construct feature space from Fourier series and like how these can be used for smoothness. Just to, I guess, remind you, so these slides, by the way, are going to be updated by the end of today. So there'll be a new version of the page, which is what I've got up here. Okay, so the idea is that you can represent functions by building them up in terms of increasingly complex sort of nonlinear features, okay? So you've got some function of x here, and my claim is that I'm going to build that up by adding together a bunch of cosines and sines, okay? So, and this L here, as it grows, these are going to become sort of higher and higher frequency, okay? So this is how I'm creating my function. So rather than just sort of talking about this in the abstract, I'm going to give an example. So let's say you have something like a top hat function, which is basically 1 on an interval and 0 outside of it, okay? So the Fourier series representation of this is going to be sine of L on L. Okay, so let's see what this looks like. So here's the function we want to represent in red. Okay, I'm going to be building these up, this red function up, using these basis functions I'm going to draw here. Okay. And I'm going to multiply these basis functions by the coefficients that I've got in this corner here, okay? So right now I've just got this thing here, which is just a constant offset, so I'm pushing this up by some amount. And then I've got basically these coefficients here, which are going to, like they're the same, it's symmetric, and they're going to multiply this nonlinearity here, okay? So what I've got to start with is just a cosine function, multiplied by this amount here, plus some constant offset, and this is the approximation I've got so far to my square function. So it's like not all that good. So let's now add some more functions. Yeah, these actually have zeros. So this next nonlinearity I'm not adding at all. Like it turns out that the coefficients here are just 0, so that's boring. So this next one I'm adding with some negative weight. You can see that if I take my cosine and I add this function with a little bit of negative weight, it's getting closer to the top hat. Okay, this next one doesn't get added at all. Then you add a few more, it's getting closer and closer to the top hat. So you can see that as you're adding more and more of these high frequency functions, with these weights here, I'm getting closer and closer to the function that I'm after. Okay. And I can continue, and then eventually, like, you can keep doing this. In fact, this sum goes off to infinity, but the weights are getting smaller and smaller, and this is getting closer and closer to the function that you're after. Okay, so this is the idea of how you're building up space functions by adding together these nonlinear features. Okay, so this is my Fourier series. So there are questions about this idea so far? No. Okay, good. Okay, so this is a function that I want to represent, but I want to represent. So that's the function after. Now remember we have a kernel function as well in the RKHS, and I'm going to use exactly the same trick to build up my kernel function. So remember that the kernel is something that takes 2 arguments. Okay. And I'm going to say that my kernel, I've just chosen it in such a way that it's a function of the difference in the arguments. So the Gaussian kernel is a good example of such a function, because a Gaussian kernel is just like the Gaussian whose argument is just the difference in the 2 inputs. So that's your standard Gaussian kernel. Okay? So given that my kernel now just takes a single argument, which is the difference in its 2 inputs, I can represent this kernel also built up in terms of these cosines. Okay? So if my kernel looks like this, which is a Gaussian, then the Fourier representation, so building up the kernel in terms of these cosines, the coefficients of these nonlinearities will also take the form of something that decays like a Gaussian. So I've got e to the minus, in this case, like the Gaussian evaluated only at integers, so L squared, divided by 2. Okay, so let's do what I did for the previous function with the Gaussian, okay? So I'm starting with just this cosine here, so it's like not all that close. Now I'm going to add a couple more sinusoids, so a couple of these features, and so now it's getting a little closer. I'll add some more, it's already extremely close, a couple more, and like here you can see that the these I guess nonlinear features multiplied by these numbers here are getting extremely close to a Gaussian. And you can also see that these are decaying as a Gaussian, right? So the Fourier series coefficients used to represent this Gaussian actually also have a Gaussian decay. So that's like an interesting feature that's sort of specific to the Gaussian here. Okay, so I've built up a kernel using Fourier series, and I've also shown how to represent functions using the Fourier series. So using these two representations, I now want to construct a reproducing kernel Hilbert space with some sort of appropriate way to control the smoothness of the functions that are in that space. So I'll describe what that means. Okay, so basically, does everyone remember this f dot notation here? So basically, like this f dot means that I've just got some vector of numbers, which might be infinitely long, such that when I take the inner product of f dot and the feature representation of an x, then I should get f of x. So I'll just write that down as a reminder. So this is what I mean by this notation. If I have f dot, and I take the inner product with the feature representation of x, which we've seen can be written k of x and dot, then that's equal to f of x. Okay, so that's the property that this f dot has. The second thing always to remember is that these k x dot, this is a function of some argument indexed by x, parameterized by x. Okay, and in particular you can write something like this: ky dot kx dot is equal to k of x and y. So basically, you can do this sort of argument here, but you can use k of y dot as your f here, and everything should work out. So it's the reproducing property. So we want these two things to hold. We want to find some representation of our function f such that this property is true, and we want to find a representation, like we want to have some sort of nonlinear set of features about x such that this property is true. And if these two properties are true, then we've got ourselves a reproducing kernel Hilbert space. Okay, so I'm claiming that you can do that if you define your f in this way here, which is these Fourier series coefficients, so these numbers that I've used to build up my function, divided by the square root of the Fourier series coefficients that I used to build my kernel. Okay, so this is what I'm claiming is my representation of my function in the RHS. Like this is my feature vector. Okay. So the inner product between these two functions is just a standard inner product between these two vectors. And I'm going to define my feature map to be the following. So it's these exponentials, so these like increasingly high frequency nonlinear functions. So remember, this is like cosine plus sine, multiplied by the square root of the Fourier series representation of my kernel. Okay. So if I define these two things, can I show that all of this stuff that I need to have hold is going to hold? Okay, so let's just check the first one. So the first one is that I want the inner product of this feature map with k to be equal to f of x. Okay, so is this true? Well, if you write the representation of f dot, like this is f divided by square root of k, the representation of k is just this, the complex exponential times the square root of its Fourier series coefficient. Like this is what we've defined. And that's convenient because we've defined it in such a way that these cancel and you just get the Fourier transform of f. So that works. Yep. So is that clear? Yeah. Okay. So now let's make sure that this second property holds, that k is itself, in a function in the space and the inner product of two feature maps is just the kernel, well, this is true as well, right? Because k of dot x I've defined just to be this, k of dot y I've defined to be this. You take, so this thing here just means the complex conjugate, which means you just swap the sign of this thing here, okay? And then you take the product of these two, the square root of k times square root of k is k. I flip the sign here, so I've got y minus x in this argument here, and this is just the Fourier transform of k evaluated at y minus x, which is exactly k of x minus y, because of the kernel symmetric, so x minus y minus x doesn't really matter. Okay, so all of the properties that I wanted to have hold are going to hold. So just a reminder from the last lecture of like why would I bother to define a feature space in this way? This is because I want the norm of my function in the reproducing kernel Hilbert space to be in some way a smoothness penalizer, okay? So remember that the norm of a function, squared in this case, is just the inner product of the function with itself. Like that's the standard definition of the norm. Now remember that these functions are just these Fourier coefficients divided by the square root of the k. Because I've got the function inner producted with itself, the square root of the k times square root of k just gives you k. And so I've just got this product of the Fourier coefficients divided by the Fourier coefficients of the kernel. Okay? So what this means is that I want this thing to be bounded. I want it to be less than infinity, because if it's bounded, then the function is in my space. If it's not bounded, it means that these sums have diverged. The function isn't in my space anymore, okay? So if the Fourier coefficients of the kernel are decaying, which they have to be, then basically what this means is that for this sum to be bounded, the numerator has to decay faster than this denominator. So that basically this top bit is going down fast enough that even though this is increasing, nonetheless this sum is converging, okay? And so basically like this can be a very strong constraint, because if this is decaying very fast, then this has to also decay very fast for the function to be in the space. Okay, so yeah, bearing in mind that my function is a sum of these cosines and sines, okay? So here is a fun question. So I've introduced the step function, and I've shown its Fourier series representation. So is this function in the RKHS with the Gaussian kernel? So who thinks that it is? Who thinks it's not? Who's confused? One person thinks it's not. Why do you think it's not?
From what you said, it's a k factor. It's a k like exponential.
Yeah.
And from I think the how do you call it? The function.
Yeah, top
it's more hyperbolic.
Yeah, it's decaying polynomial. So I will. Yep, you are right. So I will show you this trick. So here is the coefficients for the Gaussian, okay? So the coefficients of the Gaussian are decaying as something like e to the minus L squared, okay? With some other stuff, okay? So let's just say that's KL. So now let's go back a little bit. Here are the coefficients for the sinc function, okay? So these FL, and I'll put a hat on it. This is something like sine of LT, L capital T, which is the width of my top hat, divided by L pi, okay? So these are my FLs. Now the thing is that these KLs are decaying as e to the minus L squared. But these FLs are just decaying as 1 on L, because remember the sine function never decays, it just keeps going on. Okay, so but this sine L on L is decaying as 1 to the minus L. Okay, so if I've got FL times its complex conjugate divided by KL, this numerator here, that's something like L to the minus 2. And this thing here is e to the minus L squared. So this is decaying really fast, like exponentially fast. this is decaying polynomially fast. So this thing here is absolutely not going to converge. And so the top hat is not in the Gaussian RKHS. So this is like, if you can do a Fourier series representation of your function, you can very quickly find out if it's in an RKHS. So this top hat function, like it shouldn't surprise you that a function with these extremely sharp corners isn't in a RKHS that penalizes smoothness very heavily like a Gaussian RKHS does. But here you can, like, that's the intuition you should have, but you can prove it actually pretty easily as well, just by using this Fourier series trait. So yeah, I mean that's, is there any more questions about this idea for, yeah? Oh, that's clear for everyone. So just to be clear, like in assignments or exams, like you won't have to sort of know how to take Fourier transforms, but if I give you Fourier transforms, you should know how to make these kinds of arguments. So like at least to understand that if I give you this set of features, can you tell me whether a function is in an RKHS or not? So that's the important point to take away from this. Yeah, because it's like not a course on Fourier theory, but it is a course on like how to apply that. Okay, so this I guess is the Fourier features. So now I'll go forward to where we left off last time. Okay, so this was this difference in means. So the first, I guess, algorithm that I will be talking about today in detail is kernel principal component analysis. So I think perhaps most of you have encountered PCA in machine learning courses, or I hope like that's David Barber's course or Manish and UI's course, you've seen this before. So has everyone seen PCA at some stage? Yeah. So the goal of PCA is basically like if you're in some high dimensional space, like R capital D, your goal here is to find some subspace of that space that contains sort of most of the points, and sort of everything else is noise. So here I've got an example. I've got these red points scattered on a plane. The plane is done by gray dots. And this is embedded in a 3D space. And these blue lines here are the two principal axes that we get via principal component analysis. And you can sort of see that they are embedded in this plane here. And so if I were to project my data onto the plane defined by these two axes, then that would sort of contain all my data, and anything else, like maybe there's a little bit of out-of-plane noise, but I can ignore that. So one of the, I guess, biggest uses of PCA in the literature is, in fact, removing noise, because like finding the low-dimensional subspace that contains most of the variation in your data. Okay. So this is PCA. So why would one ever want to do that with kernels? Again, the idea, or one of the ideas, is this denoising idea. But because you're denoising in feature space, you're sort of finding some, some, I guess, low-dimensional space that most of your data is on. But the space is defined for the nonlinear features of your data, and not like for the original data itself. So, you know, the features of the data may be sort of very nonlinear and sort of encoding properties of the data. But this encoding is on some sort of plane, even though the data itself might not be. Okay? So a very nice example of this is if you've got handwritten digits with a lot of noise. So if you just run PCA on your handwritten digits to try and denoise them, handwritten digits in their 16-dimensional space aren't on a nice flat plane. Okay, they're on some strange manifold in that space. But if you do PCA in an appropriate feature space and then down project, you can sort of discover this manifold because in the high-dimensional feature space it's reasonably flat, and so PCA is enough to capture it. Okay. So let's say that I have, and I'll show an image in the next slide of this, but I'll first give the idea. You have some noisy handwritten digit, okay, and then you're projecting using these projection operation here, this handwritten digit onto the principal components, so the first D principal components in feature space that I've defined using like some cloud of handwritten digits in the feature space, okay? So I can project that point into feature space, but then of course, like I've got some, feature space representation of my handwritten digit, which is sort of hard to deal with. So I need to find the closest actual image in my input space to this feature space projection, okay? So remember, I've just projected this onto some maybe infinite dimensional nonlinear feature set. So this isn't, this is a very high dimensional object here. And I'm trying to find a single point whose feature mapping corresponds to this projection. Now, if you remember, the span of the feature mapping in feature space is usually a lot smaller than all of the functions in feature space. So there was an example that I used in the earlier lecture, which is the following. If you have a two-dimensional vector, x1, x2, and your feature space is something like x1 squared, x2 squared, x1, x2, right? Then if you consider this in 3 dimensions, then there will be a lot of vectors in 3 dimensions that can't be written as feature maps of these two. So one example is the vector, say f is equal to -1, -1, 1, right? Because -1 can't be written as the square of any real number, okay? And so you're going to encounter this problem a lot. You're going to project your noisy digit down into the first D principal components, but the problem is that there will correspond no single digit whose feature map is equal to this projection. So in fact, it will pretty much always be the case that this is true, okay? So that means that you can't get an exact solution. You'll never actually make these two correspond exactly, but it's still helpful to get a pretty close match, and then the digit that you get out is going to be a pretty decent answer. So how well does this work? So here is a bunch of handwritten digits. Here we've just added a whole lot of noise. Here we've denoised it using just your standard kernel PCA that you would sort of download and use from MATLAB. And here we've denoised them using PCA in a Gaussian kernel feature space. And so visually it's pretty clear that the kernel PCA is doing far better than the vanilla PCA. So this is, I guess, a motivating example. So now how do you actually do PCA in feature space? So first, just a reminder of what PCA is doing, okay? So PCA, let's just take the first principal component. What you're trying to do is to find a direction to project on, which I'm writing as U here, that maximizes the variance, okay? So basically maximizes the square of the projection of x minus its mean onto U, okay? So you're basically finding the direction of maximum variance in your data. That's what I've written here. So is that clear? And I can expand this horrible expression into a much cleaner matrix expression by just writing this as U transpose times C U, where C is the covariance matrix. So basically the sum of x minus its mean transpose, okay? So this thing here is the covariance matrix of the vector x, okay? And I can even write this compactly as x times h times x transpose, where h is basically the unit matrix minus a matrix of ones normalized by an inverse. So with a little bit of algebra, you can write this thing here as this thing here. So these x's have in their columns x1 through xn. The h's are just this centering matrix, which is the thing that has the effect of subtracting the mean on each side, and then x transpose, okay? So hopefully you've encountered these expressions before, so I'm just reminding you of them, okay? And so when you do PCA, all that you're doing, like the first eigenvector is the direction of projection that maximizes the variance. The subsequent eigenvectors are the directions of projection that give the largest variance subject to being orthogonal to the previous ones, okay? So you're finding the best variance, then you're finding the next best, then the next best, then the next best, and then you stop when the variance that you find when you do your projection is sort of small enough that you say, well, that's probably noise, and we can forget about it, okay? So this is how you do PCA. So now what happens if rather than using these x's, you're using some feature space representations of these x's? So can you still do all these operations? So remember that the main, I guess, power in the kernel methods is that even when your feature space might be infinite dimensional, if you can avoid evaluating the feature vector explicitly, but just deal with the kernel, so the inner products between the features, then you can do these sort of very powerful nonlinear algorithms in feature space without ever having to worry about the features themselves. I just realized my laptop should be plugged in since the battery will die. In the meantime, do you have questions? Is there a plug around there? Yeah. Yeah, that's happy. Good. Okay. Okay, so I want to do this now in feature space. So here's my expression in input space. Here's my expression in feature space. What you might notice is that they're pretty much the same, as you certainly would hope. Okay, so I've just taken my x's, I've replaced it with phi x. Here is my mean. Now remember that last example I gave in the previous talk, like the mean in feature space is just like the standard mean. You just use feature vectors where you would use your x's, okay? So I'm doing exactly what I did before, maximizing with the norm constrained to be less than or equal to 1 of the inner product of f and the xi minus its mean, all squared expectation, so the variance of f, okay? So nothing has changed from the linear to the kernel case, okay? So now, the trouble with these kernel expressions, of course, is that this f is infinite dimensional, these phis are infinite dimensional, and I want to write this entire algorithm only in terms of the feature mappings of my sample points, because then I can express hopefully everything in terms of inner products between these features on the sample points, which are kernels, which are in closed form. Okay? So the trick here is that my f function here is a linear combination of these centered sample points, okay, with coefficients alpha I. So why is that? So let's imagine if it weren't, then the inner product of this f, so let's write this out. So let's write f is equal to f parallel plus f perpendicular, right? Where f parallel is in the span of these centered points and f perpendicular is orthogonal to it. So then when I write f parallel plus f perpendicular inner producted with phi xi minus sum over I phi xj, let's make that j, right? This component here, inner producted with this, is going to be just 0, right? Because it's orthogonal to all of these components. So I'm just going to be left with f parallel, which is the component of f that can be written as a linear combination of these points here, okay? So I know that because I'm maximizing this expression here, any f that is outside of the linear combination of these points is just going to vanish, okay? Because when I take the inner product with these points, that component will go to 0, okay? So basically, like, I should put all of my f in this sort of basket here, because anything that I don't put in this representation, I'm just going to lose. So it's going to be hopeless. Okay? So is that idea clear? Or are there questions about this? Okay. So let's start with this. Okay. Actually, no, I will talk about this. Okay. So I talked about projecting my handwritten digits onto the principal components. So assuming that my principal component, f, has been written in this form that I've introduced on the previous slide, then it's very easy to find the projection of p of x onto the direction f, okay? Because remember that just from your linear algebra, the projection of some vector onto some other vector is the inner product with this direction you're projecting on, multiplied by that direction. So here I'm assuming that f has unit norm, okay, which when you're doing PCA it will. I'll show you later actually how to get it in unit norm. It's a very simple thing, okay? So then the neat thing about this is that when I'm doing this projection, bearing in mind that f is a linear combination of alpha j times xj, then the inner product of p of x star and xj is just the kernel, and then you basically get like this whole thing here is just a scalar because it's a linear combination of kernels. These are scalars, so you basically get like a sum of the feature maps of the x's, okay? So yeah, this projection operation can be done entirely in terms of kernels, and it gives you, as you would expect, like some weighted sum of your x's that you use when you were doing PCA. Okay. So how do I, so that's the projection trick. So how do I do PCA? So just as a reminder, how did I write my covariance? My covariance, if I'm assuming my points are centered, so covariance is equal to the sum over I, 1 on n, of xi minus the mean, right? Xi minus the mean transposed, okay? So basically, like, this is a sum of x transpose, where these x's are centered, okay? Now, the trick is that we want to do this in feature space. We want to define something that looks like a covariance in feature space so we can do PCA. And so it turns out the only, I guess, trick to doing this is a notational one, okay? So I'm going to define a notation that corresponds to this idea of XX transpose. And it's going to be this A cross B notation, okay? So how this works, so in linear algebra, if you have A, B transpose, okay? If A is a vector and B is a vector, this thing here is going to be a matrix, okay? And you can multiply this matrix by another vector, C, and because you can choose what order in which to do these operations, I can just write that as A, B transpose C, and this is a scalar. Okay? So this is like the notion of A-B transpose in linear algebra. And you can do the same in feature space, okay? You can define something which I'm going to write in feature space. Version. It's going to look like this. You've got something that looks like A cross B, okay? So this is my analog to A-B transpose. And I'm just going to say, well, these are in feature space, so these might be infinitely long vectors. But I'm going to define them such that if you take this object here and you apply it to a third object in the same feature space as B, then this is going to be equal to the feature space object A times the inner product of B and C in the feature space. So I'm just basically giving notation for doing exactly this linear algebra trick here. And I need this A-B transpose trick so that I can define covariance in feature space, okay? So all I've done is basically said, like, if I want to do something like this, like a covariance, then this is the notation I'm using when I'm in feature space. So is that clear to everyone? Yeah. Obviously. So what I've written here is the covariance. What I've written here is the feature space covariance. And you can see that I'm doing exactly what I said here. I've got basically the sum of the features of xi minus their means, and then the features of xi minus their means transposed. So this is what this notation is denoting, okay? And so because I don't want to write this out every time, I'm going to define these tilde terms here, which are just like phi of xi minus its mean in feature space. Okay, just to like reduce really dramatically the amount of annoying notation I need to write. Okay, so this is the covariance in feature space. Now I want to do PCA on this object here. Yep. Okay. So when I'm doing PCA, what do I do? So I need to basically like solve this sort of eigenproblem here, okay? Which is f lambda is equal to cf. So this is the nth principal component. This is this covariance here, okay? So at this point I'm going to start writing stuff. So remember that I've written FL as the sum over I of alpha L, so L is the principal component, I is the index of the sample point that I've used to define my covariance, times phi of xi, okay? So I've said that my f, my principal component, has to be in the span of the linear combination of the points that I used to define my covariance, okay? Because if it won't, then that component would vanish when I project it, okay? So if this is true, then what I want to do is to apply this operator C, which is 1 on n sum over I, phi tilde, this has to be phi tilde, I forgot my tilde is xi, cross phi tilde xi. So I want to apply this to f, okay? So CFL, right? 1 on n sum over I, phi tilde xi, cross phi tilde xi, applying to FL, right? Now here I use this trick, A, B, C is equal to A. Okay, so I'm using now the fact that if I take the tensor product, so this A cross B or AB transpose, and apply it to C, I get this A multiplied by this vector BC, okay? So here I've got a sum of terms, a sum of these tensors, and each of these terms in the sum I'm applying to this FL, okay? So then I get a sum, n sum over I, phi tilde xi. So now I'm taking this inner product here, phi tilde xi inner product with FL. Okay, so just using this expression here. Now, this is equal to 1 on n sum over I, phi tilde xi, times, so what's this thing here? So FL, I've said it's up here. It's sum over I, alpha Li, phi xi. So let's just plug that in. So you've got sum, I'm going to use j because I've used I already, sum over j, alpha Lj. And then I've got the inner product of phi tilde xi from here. And then the phi tilde xj's from here. Phi tilde xj. Okay? Now I've got here an inner product between two feature maps, and this is just equal to k tilde xi xj. So I've used the k tilde to denote that I'm taking the inner product between these two centered feature maps rather than the inner product between the two uncentered ones. But you can find, and I'll leave that as a very short exercise, that k tilde is just HKH, where H is that centering matrix we use when we define the covariance. So C is equal to XH, X transpose. So it's exactly the same H. Yeah. Okay. So the upshot is that I've been able to show that C times F is a weighted sum of feature maps where the weights are defined in terms of these kernels. Okay. So this is what I've got on this slide. So where does that leave us? So I'm going to write I'll erase all of this stuff here. So this leaves us with FL lambda L is equal to this, right? Because I've said FL lambda L is equal to CFL. I've said that CFL is equal to this expression here. Okay, so that means FL lambda L is equal to this expression here. Okay, and remember that FL is equal to sum over I, sum over I of alpha Li phi of xi. So that times lambda L is equal to this. Okay. So this unfortunately didn't answer my question, because what I've still got here is these feature maps of x. I forgot to center it. On both sides of my equation. So this thing here I've written in terms of kernels. So this is k tilde xi xj. So here I've got a kernel expression, but here I'm still in feature space. So I've got a sum over feature maps is equal to a weighted sum over feature maps with these weights here. Okay? So what I want to do is to have a problem that I can solve only in terms of kernels. So only in terms of inner products between the feature maps. But what I have here on both sides of the equation are still feature maps and not kernels. So I need to do something here. So what I should do is basically to take these expressions here and take inner products of both sides with feature maps, okay? So here I've got a sum of feature maps. If I take the inner product of this side and this side with, say, a feature map of xq, then the inner product of this with the feature map is going to be the kernel, the product of this with the feature map is going to be the kernel, and I'm going to get a whole bunch of kernel functions, okay? So that's basically what I'm going to do. Okay, so this is basically, let's take the inner product of both of the sides of this with the feature map xq. So let's say that I'll start up here, FL lambda L is equal to CFL. So that means that FL feature map xq lambda. This is why I needed to plug the laptop in. Yeah. Lambda L is equal to then the inner product of feature map xq with CFL. Okay? So the left-hand side is pretty easy. So you've just got the inner product of sum over I, lambda Li, phi xi, right, and phi xq, which is just sum over I, alpha Li, k, and these are all tilde, xi, xq. Okay, so now this is good. So my left-hand side here, I've now written entirely in terms of kernels. Okay, and then so I've basically got a sum over I of alpha Li times a vector of x and I and x at q. Okay, and I can do that for every single q. So then I basically get, this is just for a single q among the n that I have available to me. So I can now write a more general version of that, which is basically something like k tilde alpha. Okay, so this is the k between every possible xi, xq pair times lambda L, alpha L lambda L. Okay, because this is like a vector multiplication now I do that with every xq, I get a matrix vector multiplication. Okay? So this is what I've, like, this is my left-hand side now, f lambda L multiplied by all possible feature maps of xq. So now this gives me a left-hand side in terms of a kernel matrix. Okay? And now I can do the same for the right-hand side. So remember, the right-hand side, I'd said that CFL is equal to this expression here. Okay? So now I can multiply this right-hand side with every possible phi of xq as well. Okay? And so then what I get out is something which amounts to the square of the kernel times alpha L. Okay? Because remember, I've got a kernel from here. It's the square of the kernel because I get another kernel when I take the inner product of these phi xi's with every possible phi xq. And so then I get basically kernel squared alpha L. Okay? Now I've got a kernel on this side and I've got the same kernel matrix on this side, so I can cancel one of them. Then I just end up with alpha L lambda L is equal to k tilde alpha L. Okay? So now this is an eigenvalue problem in terms of the centered kernel matrix. So I never have to worry about the feature map anymore. I can do everything in terms of inner products of the feature map. My solution is then a linear combination with weights alpha of the mapped points that I use to define my covariance. So my solution FL, just sum over I alpha L of the feature map of XL. Okay, so this is how I do PCA in feature space while never looking explicitly at any of the feature maps. So there are questions about this proof. So all of the proof is in the slides. So yeah, you can perhaps look at it again. But you can sort of see that like all I've ever had to do is like very elementary, like linear algebra type operations. All I've had to do is basically like take inner products, and yeah, there's nothing that happened here that was very like exotic or difficult. So one thing I said that I would show you is that remember when we want to project onto the principal components, we need to make sure that our f has unit norm. Okay, so how do we normalize f? We just have to divide by its norm. So what is its norm? It's actually very easy to compute. So remember that the f can be written as the inner product of this and itself. Okay. Now, I can just take these alphas outside, and I then get a sum over alphas times the inner product between the centered feature maps at x. The inner product between the feature maps is just the kernel. And so basically then I have the norm being equal to 1 amounts to basically saying that the alpha transpose times the centered kernel times alpha, which I know because of kernel PCA is n times lambda times alpha, because remember kernel PCA means that I've already established that alpha times lambda is k times alpha. So k times alpha is lambda times alpha. So I've got this expression here, n times lambda times alpha is 1. So if I replace the alphas that I get by solving this eigenproblem with these same alphas divided by square root of n, which is number of samples I use for my covariance, times lambda, then, and I use these alphas in kernel PCA, then the functions have been normalized to have unit norms. So everything that I've needed like to make my projections easy is true. Okay? This is this unit norm thing. Okay, so that's, I think, kernel PCA is probably one of the sort of simplest and most classic kernel algorithms. And it sort of kicked off the trend in kernel methods of saying, well, the moment I have an algorithm which I can define in terms of inner products, I can replace the inner products with kernels, and then I can write a paper and get published. So there was like kernel CCA, kernel PLS, kernel Fisher discriminant, and on, and then people ran out of easy targets and then moved on to other things. But anyway, kernel PCA was the first. So yeah. So a slightly harder algorithm, but in this sort of same spirit, is ridge regression. So this is the algorithm that I started the presentation with, which is basically like, if I'm given some kind of points, y, and I've got a bunch of x's, and I want to make a smooth function through them, then ridge regression is one way to do that. So it's a way of sort of defining a function that's reasonably smooth and that doesn't make too much of an error on all of these points. So it turns out, I mean, ridge regression is something you can implement in the line of MATLAB. So it's actually a very easy algorithm. I'm going to just derive it here first, like normally, and then in feature space to show you how it works in terms of kernels. Okay. So let's check the time. Yeah, good. So what is good old vanilla ridge regression? Well, let's say you have a matrix where each column is an observation in RD, so a d-dimensional vector. Okay, so you've made d observations. Maybe these are images or some like object, and from these objects you're trying to predict a label. A number. Okay, so maybe whatever sort of feature of these images you care about. Okay. And so in training, you're given a bunch of example images and a bunch of example predicted numbers. You're now trying to find some function to predict the number corresponding to some new image. Okay? So one way to do this is to basically find the projection of these images, so x transpose times the vector A, which minimizes the average squared error. Okay, so this is what it should be predicting. This is what it's predicting. And you also add here a ridge term. And this term here basically stops you from running into trouble in high dimensions in a way that we're going to see very shortly. And in kernel methods, we're going to also see, or we've already seen, in fact, that this is a way of enforcing the smoothness of the function that you're using for your prediction. Okay. So these are like the two terms that matter. The error that you make, how smooth your function is. This thing here is going to control the trade-off. So if this lambda is really big, then you're going to care very much that the function is smooth. If the lambda is very small, you're going to care very much that you don't make too many mistakes. Okay? So these are the sort of two things that you can control. And as usual, it's a lot easier when you write this expression in a linear algebraic way. So here, this is my y, that's my vector of the things I'm trying to predict. This matrix here is my matrix of observations, and this A is the vector that I'm projecting onto. Okay? So this is my ridge regression. Okay. And you can solve now for A. So what do we do? Let's expand out this sum here. So you've got first this norm. You've got your y transpose y. You've got your y transpose xa, the cross term. You've got your A transpose x, x transpose A. And then you've got this term here, which is basically A transpose A. Okay. Now you can now join these two terms together. So you've got this term stays the same, this term stays the same. Now you've got A transpose, x, x transpose, plus lambda times the unit matrix times A. Okay. So now I want to solve this thing for A. So what is the A that makes this as small as possible? So you can do this either by taking derivatives or by another way, which is the one I'm going to use because I think it's clearer. So what I can do now is to define something which is basically the square root of this matrix here times A. So a matrix square root times itself is equal to the original matrix, okay? So basically I'm taking this big object here and I'm writing this as just B transpose B, where B is A transpose times square root of this matrix, okay? So that's what I'm doing here, okay? So where before I had A transpose X, X transpose plus lambda IA, now I've just got B, B transpose. Okay. Here, I had an A before, so I've got this expression here, which is X, X transpose plus lambda I minus half B. Okay. And then Y, Y transpose stays exactly as it was before. It's just Y, Y transpose, Y transpose Y. Okay. So what this term here, these last two things look like, is almost the difference in, well, the norm of a difference, okay? So this is one of these things where you you can complete the square. So you can say, well, a squared minus 2ab plus b squared is going to be able to compress into like a minus b all squared. And then you're going to have like this extra term that you're going to have to add because like the square isn't quite complete, okay? So you've got your yy transpose here. Then I've said, well, these two terms look like this minus b all squared. But the trouble is that I've left out then this last thing, which is basically this yx transpose xx blah blah times itself, okay? So if I expand out this squared, I need this term times itself. But that wasn't in my original expression, so I'm adding it here, or subtracting it here. Okay? So what do I have here? I have yy transpose. I've got this function of b, and then I've got this term here, which has no b in it. But b is this term here is the only one I actually care about, because this is the only one which contains the variable that I'm trying to solve for. This thing here, it doesn't matter what I do to b. This thing here, neither, okay? So what can I do? To minimize this whole expression, I just set b equal to this, because then this whole term is 0, that's the lowest it's going to get, okay? So I set b equal to this. Now remember, I defined b to be this to the half times a, so I just plug that back in. So that means that a is equal to this to the minus 1 times xy, okay? So this is the solution to my ridge regression problem. This is what's going to minimize this term here with respect to a. So is that line of reasoning clear to everybody? Yeah? Okay. So this is ridge regression. I mean, I'm sure you've seen this one before. The problem with this solution here is that the form that we have for a is not actually all that revealing. There's a much more useful form, particularly when we go into feature spaces, which is that you can write this a as a sum of the columns of x. So basically, like a is a sum over, like some weighted sum over the training observations that you've made. And this is a much more useful form when you start moving into feature spaces, because then your feature map of A is a weighted sum of the feature maps of your training points. And that's like the form that you actually want it to be in. Like if I give you something like this in feature space, you've got a covariance in infinite dimensions, which you're inverting. The whole thing's a terrible mess, okay? So this form here, is not the kind of form I want it in. What I want my answer to be in is this kind of form here, where I've taken a linear combination of some set of weights times my training x's, okay? So how do I get my solution in this form? Okay, so here is where things will get slightly tricky, but not too tricky. Okay, so let's say that we've got d dimensions, and let's say that the examples that we see are very high dimensional compared to how many training samples we have. So like an image might be 5 megapixels or whatever in size, and you might have 100 of them. So obviously here d is much bigger than n. When you start moving into feature spaces, this will get even worse. So this will be like infinite, and n will be 100. Okay. So remember what this x is. This x is your training data stacked into columns. Okay. And I'm doing a singular value decomposition of this x, okay? So I'm representing it as an orthogonal matrix times a diagonal matrix times another, part orthogonal matrix transpose. So the reason it's part is because this thing here is d by d, but x is d by n. So n, v has to be d by n, okay? So this U matrix, all of the columns are orthogonal. It's a singular value decomposition. That's what the property of it is. This S here, because x is only d by n, there can only be n non-zero singular values. But this is a d by d matrix. So the first n diagonal elements will be non-zero, and then I'm going to fill everything else with zeros because there's no more non-zero singular values. Then this V here is going to contain in its first columns the, I guess, non-zero singular vectors, or the singular vectors corresponding to the non-zero singular values here, and then everything else is going to be zeros, okay? So this is my singular value decomposition, okay? So if I use this singular value decomposition and I plug it into this expression here, then I'm going to get the answer that I want, okay? So I'm going to do this on the board because it's easier than trying to do it on a projector. But this is, again, like it's all in the notes, so just focus on the proof. Okay, so what is my A? My A I've written as XX transpose plus lambda I inverse XY. Okay? So this is what I'm starting with. So this is equal to now, at this point, XX transpose, I know what X is, it's US V transpose. V transpose V is just going to give me like a unit matrix and a bunch of zeros. So what I can do is I can write this as U S squared U transpose, because the zeros are going to be in the same place as the S when I do my V transpose, plus lambda I inverse U S V transpose Y. Okay? So all I've done in this first line is to replace my X with its singular value decomposition here. Okay? Now here's the next trick. Because U is an orthogonal matrix, its inverse is its transpose. Okay? So that means that I can basically use the fact that, you know, AB inverse, like I can take these U's out of the inverse just by transposing them and swapping the ordering. So I'm using here that U inverse is U transpose because U is orthogonal. I'm using also that AB inverse is B inverse A inverse. Okay? These are the two properties I'm going to use in the next line. Okay, so I use these two properties. So I'm getting U S squared plus lambda I inverse U transpose U S V transpose Y. Okay? So these U's are coming out of the inverse using these two things here. Okay? Now this thing here is just the unit matrix. Okay? So now I've got, let's write that down. U S squared plus lambda I inverse S V transpose Y. Okay. So now the next step is to take the S to the other side, which I can do because this is a diagonal matrix with zeros. This is a diagonal matrix because it's the inverse of a diagonal matrix. And diagonal matrices commute. So I can do US S squared plus lambda I inverse V transpose Y. Okay. Now I can add S V V transpose, right? S squared plus lambda I inverse V transpose Y. Why can I add these? That's because the VV transpose is just a unit matrix in the top left corner and zeros everywhere else. And the unit matrix in the top left corner corresponds exactly to the top left corner where this S is non-zero. So this times S is just equal to S, okay? And so now what we have, USV USV, I got it the wrong way around, it should be V transpose V. So USV transpose is X, okay? And then I've got, oops. And then I've got the remaining guys here, which is V S squared plus lambda I inverse V transpose Y. Okay. So this so far has actually given me the answer I'm after, because this whole thing here is just a n by 1 vector. And so I've got this matrix here, which has the columns of, like, each column of this matrix is a training point. And then I've multiplied this by an n by 1 vector, which is just a linear combination of the columns of the matrix. So this has given me, in fact, the form that I want here. Okay, a series of tricks. So again, like, what I've done here is just I take the SVD and then I do some basic linear algebra. Nonetheless, it's not exactly useful to see something like this, because I'm still writing everything in terms of all of the various singular components of my x. And what I'd really like is to have some expression for these weights, which are actually in terms of the x's themselves. So like right now with this thing here, I have to do an SVD to solve for these coefficients, and that's really ugly. Okay, so let's just bear in mind all of these steps, but let's just stick to this expression down here for a little bit and see if we can't make that cleaner. Okay, so all of this stuff I will remove. Okay, so I'm starting with this, which is, I'll start up here, vs squared plus lambda I inverse v transpose y. Okay. Okay. So this thing here, I'm going to write, remember that this is equal to v tilde and a bunch of zeros. S squared plus lambda I inverse. And then, yeah, v tilde transpose, bunch of zeros, y. Okay? So basically, and remember that this term here is just s tilde plus squared, plus lambda I, 0, 0, and then lambda I here. Okay? But this lambda I here is wiped out by these two zeros here. Okay? When you do the matrix multiplication. So what you can actually write this as is something a lot smaller, which is basically just like, bearing in mind these zeros wipe out everything else, you've just got v tilde times the s tilde squared, so only the non-zero entries of s, plus lambda, and now a much smaller I, so this is a d-dimensional I, I'll put a d there, this is an n-dimensional I, inverse, v tilde squared, v tilde transpose, y, okay? So I've basically taken away all of these all of these things that are just wiped out by the zeros, okay? And now v tilde is just this part of the matrix here, and v tilde is orthogonal. So I'm again going to use these two tricks to take the v tildes inside, and then I'm going to get inside the inverse, and so I'm going to get v tilde s squared v tilde transpose plus lambda I n-dimensional inverse, okay, times y. Now, what's this? If you just look at this expression here, this is just x transpose x, right? Because you've got v s squared v transpose. So that's just, rather than the outer product, it's just the inner product of x transpose. Plus lambda I inverse y. And this is a much nicer expression than the one we started with, because now, rather than writing it in terms of these singular vectors and singular values of x, I'm able to write the coefficients only in terms of the x matrix itself. So that's a lot easier. Okay? So this is my solution now. So let's go to the solution. So you can see all this is in the web page.